Today, we're going to trace a line from a 100-year-old crisis in pure mathematics, straight to the device you're watching this on right now. It's an incredible story about certainty, about structure, and a brilliant idea that changed the world in ways nobody could have ever seen coming.
We all trust math, right? 2 plus 2 is always 4. It's solid. But what if I asked you to prove it? And then, what if I asked you to prove your proof? How far down does that rabbit hole go? This very question, what are the absolute rock-solid foundations of math? Well, it became a full-blown obsession for mathematicians in the early 20th century. You see, as math got more and more powerful and abstract, things started getting weird. Paradoxes and contradictions started popping up. It was kind of like building this magnificent skyscraper, only to suddenly worry that the very ground it's built on might be hollow. The entire structure of mathematics felt like it was at risk of collapse if someone couldn't prove once and for all that it was totally consistent.
So yeah, this was way more than just some academic puzzle. For the people involved, this was a quest for the very soul of reason itself.
Enter David Hilbert, a giant in the world of mathematics. He stepped up with this incredibly ambitious plan, which we now call Hilbert's program. The goal? To formalize all of mathematics into one single system and then prove that the system could never, ever contradict itself. He essentially wanted to build a machine of pure logic that would make math secure forever. But while most people were busy trying to follow Hilbert's plan, building more and more complicated proofs, a young logician named Gerhard Gentzen had a totally different idea. He thought, maybe the problem isn't that we need better proofs. Maybe we need to understand what a proof even is.
And honestly, his approach was radical. Instead of just writing proofs to prove things, he started treating the proofs themselves as objects to be studied, like a biologist studying a cell or an astronomer studying a star. He basically invented a whole new field, proof theory, just to analyze the anatomy of a logical argument, its bones, its structure, its fundamental patterns. Before Gentzen, logic systems were, well, they were clunky. You started with this huge, long list of axioms, things you just had to accept as true, and a few rules to move them around. But Gentzen's new systems were different. They focused on a handful of simple, intuitive rules for reasoning. They were elegant, and they felt a whole lot closer to how we humans actually think.
And by studying proofs in this totally new way, Gentzen found something profound, a discovery about a little step in a proof that logicians call the cut rule.
So, what on earth is a cut? Okay, the easiest way to think about it is to imagine a proof is a journey from A to B. A cut is when you use a little helper statement, a lemma, to get there. It's a valid move, for sure, but it's basically a detour. It makes the path from your starting point to your conclusion longer and more complicated than it needs to be.
And this is where Gentzen's genius really comes through. He proved something called the cut-elimination theorem. What he showed was that any proof that uses these cut detours can always be transformed into a direct, clean proof that doesn't use them at all. This was huge. It meant that, at its core, logic is simple. Any true statement has a straightforward, elegant proof hiding inside it. No complicated workarounds needed.
This was a massive win for the foundations of mathematics, but this deep dive into the pure structure of logic, it was about to have a side effect that no one, least of all Gentzen, could have possibly imagined.
Okay, so get ready for the big twist in our story, because it turns out that when you stare at the structure of a logical proof for long enough, you start to see something that looks incredibly familiar to us today.
That's right, the abstract patterns of pure reason that Gentzen uncovered turned out to be the exact same patterns that make computer programming possible. The structure of a logical argument is the structure of an algorithm.
This shocking connection was formally worked out decades later, and it's now called the Curry-Howard correspondence. It reveals this absolutely mind-blowing one-to-one link. A proof of a logical formula is, structurally, the exact same thing as a computer program.
I mean, just look at how neatly this all lines up. A logical statement? That's like a data type in programming. A logical proof that gets you from one statement to another? That is literally a program that transforms one type of data into another. And here is the real kicker. Remember Gentzen's cut elimination? How he got rid of the detours to make a proof more direct? That is exactly the same thing as code optimization, making a computer program run more efficiently.
So, what does all this mean for us, right now? Well, it means this century-old quest for mathematical truth isn't just some historical footnote. They're not just in textbooks. They are absolutely everywhere. The very architecture of logical thinking that Gentzen mapped out is now the invisible foundation of our entire digital world.
Seriously, every single time you run an app on your phone, every time your computer processes data, it is following the fundamental rules of logic that were first discovered in a search for pure, abstract certainty. It's this beautiful, unexpected connection between a proof and a program. And it just goes to show that the most abstract quests for knowledge can end up shaping our world in the most concrete ways. It really makes you wonder, doesn't it? What other hidden structures are we finding today that will end up building the world of tomorrow?